So I advertised this talk by two different names to two different groups of people. Um, okay, so for Mueller, for SRB measures, and this SRB measure is just the fractal limiting stationary distributions of chaotic systems. So the two titles are actually the same thing. Okay, so let's start. Well, let's start with motivations, okay, and define the problem. Let's say this manifold M has dimension M. So we use big M to denote both the manifold and this dimension. Let F be a diffeomorphism on this manifold. And let this phi be a function on M, which will be referred to as the objective function or the observable function. Okay, this phi is typically smooth. Okay, the SRB measure is denoted by rho. This is defined as the limit of pushing forward a Lebesgue measure. Okay, so this M is Lebesgue. Okay. You can see that this rho, this SRB measure, corresponds to the particular dynamical system you choose. So once you perturb the dynamical system, you obtain a new measure, a new SRB measure. And the goal of this talk is to look at how the perturbations in F would relate to the perturbation in the SRB measure. Okay, and this turns out to be a linear relation, and this relation is called the linear response. And our goal is to develop an algorithm to compute this linear response. Okay, so we may assume that this F is actually parameterized by some parameter of dynamical system gamma, and then a perturbation in the gamma causes a perturbation in F, which further causes a perturbation in the SRB measure. Okay. So maybe this is better. This problem is actually of practical interest. For example, you can imagine that your F is the airflow, and your phi is the drag or the lift. So you want to look at, and your gamma describes the geometry, and you want to look at how changing the geometry would affect your performance of your airplane. Okay, so you can see that this derivative or this linear response is very important for many numerical tools used in a lot of disciplines. Okay, so we want to develop an algorithm to compute this linear response. Okay, so wait a second. Okay. All right. So let's look at some definitions. Okay, let's say this F, we're going to make the simplest assumption. We assume F has a compact and hyperbolic attractor. K. And hyperbolicity is just the typical model used for a chaotic system. This means that for any x belongs to K, this tangential space can be split into two parts, the unstable subspace plus a stable subspace, which means that there exists a lambda from 0 to 1, and if we constrain the push forward operator on vectors to the unstable subspace, and if we push forward backwards in time n steps, then this decays exponentially fast, where this norm is the operator norm. Okay, this operator norm is induced by the Riemannian metric on the manifold. Okay, similarly, for the stable manifold, if we constrain the push forward operator onto the stable manifold, and push it forward into the future n steps, then this also decays exponentially fast. Okay, so this explains hyperbolicity. And we also use U and S. So this stands for unstable and stable. We also use that to denote the dimension of the unstable and stable subspace. So U plus S equals to the dimension of the manifold M, which is also the degree of freedom of our dynamical system. And I also said that K is the attractor. This just intuitively means this set attracts trajectories. A trajectory is denoted by xn, okay, where it satisfies this inductive relation, xn equals to f of xn. And we're going to introduce another notation, capital X, as our perturbations on the dynamical system, but composed with f inverse. So the reason we introduce this notation is because delta f at xn is in fact very inconveniently a vector in the tangential space around xn plus 1. So there is a mismatch between the two subscripts, and it's very inconvenient. However, if we use this notation of big X, then this equals to, by our definition, x at xn plus 1, and we also denote this by xn plus 1. And you can see that these three subscripts matches each other. Okay, so it's just for convenience. Okay. All right, let's define the SRB measure, okay, more carefully. Okay, so SRB measure is the model for fractal stationary measures of chaos. And by fractal, this just means there are many non-smooth, non-differentiable quantities, and those later are going to pose a lot of difficulties. Okay. And this SRB measure is due to Sinai, Ruel, and Bowen, where Bowen is a Berkeley professor. Okay, so rho is SRB if rho is, first of all, F invariant. Okay, this means that the measure of rho, the measure of the preimage of a set under rho equals to the measure of this set for any measure of the set. Okay, so once rho is invariant, if it wants to be SRB, it should satisfy either of the following characterizing properties. The first is, of course, our definition. This rho is the limit of Lebesgue, of pushing forward Lebesgue measures. Okay, that's the first characterizing property we're going to use. The second characterizing property is that this rho has smooth densities on the unstable manifold. Okay, this unstable manifold going through a point X is defined as the collection of points Y, such that if you evolve the dynamical system backwards in time, and you also evolve backwards in time starting from X, then these 2 points get close to each other. Okay, so you can show that this VU is smooth, is a smooth manifold, and it is also tangential to the unstable subspace, VU. Okay, so for an F invariant, so for a stationary measure satisfying either of the characterizing properties, we know that this measure is SRB. Okay. Well, actually, can you see my writing clearly? Yeah. Okay. Okay. No, that's fine. Yeah. Okay. That's fine. Let us look at the linear response formula. Give it a formal derivation first. Okay, so to derive this linear response formula, we should first look at how each individual trajectory is affected by a perturbation in F. Okay, so we can pick one trajectory and fix the initial condition, make a perturbation to the governing equation, and see how this one trajectory is perturbed. Okay, so that can be written as delta xn. So this is the change in the n step. This equals to the summation over k from 0 to n. Okay. You first take the perturbation at the k step, and then you push forward it n minus k step, and now this is a vector in the tangential space of xn. Okay. And then at the n step, you collect and add all the perturbations propagated to this step. So this is so-called using the law of superposition or the Duhamel's principle. It's a typical way to write out the solution of linear equations. Okay, so once we know how the trajectory is perturbed, we can write out how the averaged objective over a finitely long trajectory is. Okay, so let this phi bar be the average trajectory, averaged over a finitely long trajectory. And this equals to 1 over n, summation n from 0 to n minus 1, delta xn. So this is a vector, and we can use that to differentiate a function. Okay, this means to differentiate a function where this phi n is defined as constraining this phi to an open neighborhood of xn. Okay, so this capital N is the trajectory length. And this is actually a pretty bad formula because immediately we notice that the perturbation just diverges. Okay, that would be expected because of the butterfly effect. Basically says that most kind of perturbations you make would give you a divergent trajectory from your original one. However, it turns out that we can remedy this divergence by taking average according to the initial conditions distributed according to the SRB measure. Okay, and that would make the formula converge. This means that we can write out the linear response as delta rho of phi equals to rho delta phi bar. So these are the perturbations in the average over a trajectory. So we're doing a lot of illegal change of illegal operations here, like change of limits and things like that. So, but eventually we get a formula that this equals to rho okay. This equals to the summation over n larger than 0 rho of pushing forward x n steps and use that to differentiate phi n. Okay, and this result was proved by Ruel. He says that although we're doing something illegal in the middle, but eventually he shows that this summation actually gives you the derivative that you're interested in. However, this is actually a very bad formula because we immediately lose the kind of ergodic theorem kind of situation because the divergence in one trajectory tells us that we cannot take the average over one trajectory and use that in place of the average over a stationary measure. And we want to recover that. Okay, and losing this kind of ergodic theorem kind of situation makes a lot of algorithm slow. So the algorithms based directly on implementing this linear response formula typically suffer from high computational cost. For example, the ensemble methods or some operator-based algorithms. Those algorithms are all based basically directly on implementing this linear response formula. And because of the bad convergence behavior of this formula, these algorithms are typically slow. Okay, so we need better algorithms. Also, we also need better analysis. Remember that when we write out this summation, we haven't even shown that this summation converges. Okay, so we want to show that this summation converges. So one thing we're not going to do is to show this equivalence. Okay, we're not going to show this equivalence, but we want to show the summation of this formula converges. And from this convergence proof, we're also going to get a hint of how this equivalence was originally proved. Okay, so for both the goal of computation and theoretical analysis, the first step to do is to decompose the linear response into two parts. Okay, so basically we decompose this X into stable and unstable parts, and then we add and subtract some unstable parts. So this means that this equals to n larger than 0, rho. We push forward the stable component of S, n steps, use that to differentiate phi n, and then we subtract for negative n's with the push forward of the unstable component of u backwards in time and use that to differentiate phi n. And then we plus for all n belongs to the integer integration, we push forward n steps xu, use that to differentiate phi n. Okay, so you can see that the second summation cancels with the negative n's in the third summation. So this recovers the linear response formula. And the reason I want to write it like this is because I want to treat the first two parts as a whole. And this is what I define as the shadowing contribution of the linear response. The last summation is what I define as the unstable contribution of the linear response. And we will deal with each part separately. Okay, we will show the convergence of each part and develop an algorithm for each part. Okay. Yeah, so if you have questions, just please stop me at any time. Okay, the first thing to do is to compute the to deal with the shadowing contribution. Okay, we can apply the variance of the SRB measure. This means that we can compose the integrand with f inverse with f to the minus nth power, and that would make this subscript minus n. It would make this subscript n minus n, which is 0, and we're going to neglect the subscript 0. It's going to make this minus n. It's also going to make this subscript disappear. Okay, so now this shadowing contribution equals to rho of summing positive n's, pushing forward xs, and subtract summation over negative n's, pushing forward, but this is backwards in time, xu. Okay, so now we first get this vector and use it to differentiate the objective function, and then we integrate according to the SRB measure. And this, you can see that this is a vector at the 0 step. And we define this as V, which is the shadowing direction. We define this as the formula for the shadowing direction. Okay, so the way we obtained this shadowing direction, let me draw a picture, is to assume this is your step n, and this is your step 0, this is some future step. The way we obtain Vn at the n step is to first take the stable components of x0 and propagate it to step n. And we also take out the stable component of the perturbation at the first step and propagate it to step n. And for future steps, we take out the unstable component and propagate it backwards in time to step n. And then at step n, we collect and add up all of these perturbations propagated to this step. So what we do to obtain this shadowing direction is actually we first split the perturbations into stable and unstable parts, and then we apply the law of superposition. Okay, so nevertheless, this is a strange way of applying the law of superposition, and it should not be very surprising that this V is also describes the propagation of perturbations on a trajectory, but it is just of a very special kind of trajectory. Okay, and this leads to a new characterization of this, well, not new, but this leads to another characterization of the shadowing direction. That is, this V is the only bounded inhomogeneous tangent solution. Okay, and by inhomogeneous tangent, this means that this Vn star equals to the push forward of Vn plus Xn plus 1. This equation, it just means that this V, it describes the propagation of a perturbation of one trajectory. Okay, and the boundedness of V means the existence of shadowing trajectories. Okay, let me draw a picture. So assume this is one trajectory of your dynamical system. If you make a perturbation to the governing equation and start from the same initial condition, you typically end up with a trajectory diverging exponentially fast from your original one. However, the shadowing lemma tells you that you can find a trajectory, although starting from different initial conditions, and it satisfies a perturbed governing equation, but it always lies close to your original trajectory. And this difference between these two shadowing trajectories is V. This is the shadowing direction. Okay, and the existence of shadowing trajectories is proved rigorously by the shadowing lemma, and this result is due to Bowen and Anosov. So Bowen, again, is the Berkeley professor. Okay, so we can find shadowing trajectories. And in fact, we can not only shadowing trajectories, we can do better. We can also shadowing the entire attractor. Okay, this means that the new dynamical system can be mapped to the old dynamical system by a conjugacy. Okay, this means that this perturbed dynamic F plus delta F, this equals to some map J composed with F composed with J inverse, where this J, of course, depends on your perturbation. Okay, so the caveat of this conjugacy is that this conjugacy map is not smooth. It's not smooth. In fact, it is not differentiable. In particular, it's not smooth enough to preserve the absolute continuous of measures. And this means that if we push forward the old SRB measure via this conjugacy map onto the new attractor, we still get a stationary measure. However, that measure would no longer be SRB. Okay, and then we need to account for how much the new measure is different from SRB. Okay, so that was Rouel's work, and this is how he proved originally that the linear response formula actually gives you the correct derivative. Okay, so we're not going to show that, but nevertheless, we convinced you that the unstable contribution accounts for, so the shadowing contribution accounts for the change in the location of the attractor. The unstable contribution accounts for the change of basically how different the measure is from SRB. And we convinced you that, at least for theoretical purposes, the decomposition into shadowing contribution and unstable contribution is natural. Okay. In fact, it turns out that it is also a natural decomposition for computational purposes. And one of the first reasons that it's natural for computation is because this V, this shadowing direction, can be computed very efficiently. Okay, that leads to our next topic, which is to compute this V. Okay, so remember when we define this V, we define it by this complicated formula. However, it is not a good idea to directly recover this complicated formula. Rather, we seek to recover the characterizing properties. There are two of them. The first is that this V is bounded. The second is that this V is inhomogeneous tangent solutions. Okay, so we develop an algorithm to recover these two characterizing properties and hence find the shadowing direction. Remember, the first property is boundedness, and due to the work of Wang, Qixi Wang, and Patrick Blonigan, it says that basically the boundedness can be mimicked by this minimization over the L2 norm, small L2 norm of V. Okay, and then it's my work to say that the fact that V is a homogeneous tangent can be written in the form that V belongs to, so we can write the space of all inhomogeneous tangent by a particular inhomogeneous solution plus the span of all homogeneous tangent solutions. Okay, where this V prime is an inhomogeneous tangent, is a particular solution, and this E, it is supposed to be all homogeneous tangent solutions, but not exactly. I did some reduction in here. Okay, this E is, first of all, it has dimension U, not M. So I did a reduction here. Okay, and this U can, for certain situations, be much smaller than the dimension of the system. And this E is a collection of homogeneous tangent solutions, means that En plus 1 is the push forward of each columns in En. Okay, and we know that if we push forward a homogeneous tangent solutions forward in time, the unstable component outgrows everything, and hence in the long time, this En approximates the unstable subspace. Okay, so notice that the dimension here is only U. And this is a reduction in the computational cost because, and this is why my work is good, because instead of searching the entire space of inhomogeneous tangent solutions, we only need to search for a subspace, which has dimension much smaller of the entire space. Okay, so this reduces computational cost, and we also need to show that this reduction still suffices to find a good enough shadowing solution. Okay, that is because the way we obtain this V prime is by solving it forward in time. And the only reason causing the divergence in V prime is because of the unstable component. And that can be removed by something in here, which is the approximated unstable subspace. Okay, so this is both a significant reduction, and it also suffices for finding still a good enough solution. Okay, and this algorithm is called the non-intrusive least squares shadowing algorithm. So this refers to this, and least squares refers to their idea. And in fact, when U is much smaller than M, we can approximate the linear response by only the shadowing contribution. It's not hard to imagine because when U is much smaller than M, the unstable contribution, you can somehow model it and say the unstable contribution is small. Okay, so you can approximate higher linear response by only the shadowing contribution, and this makes the Niels algorithm an approximate algorithm for the linear response. Okay, it is currently it is the actually it's very fast. It's actually the only algorithm that has been applied to systems with dimension over 1,000,000. And it is still the fastest algorithm, and it is also easy to implement because that requires only tangent solvers. Okay, and the non-intrusive shadowing algorithms are very well developed right now. I gave also a continuous a version for continuous time systems, and also me and Bronigan developed adjoint versions of the systems which are suitable for cases with many parameters. Okay, so that finishes our treatment on the shadowing contribution. Okay, the next step is to deal with the unstable contribution. The first part is to perform integration by parts and change of measure. I'm going to explain that in a minute. This is due to physicists, and the particular name worth mentioning is Gallavotti. Okay, so this unstable contribution, let me remind you, it equals to summation over n belongs to all integers, rho of pushing forward the unstable component of x and use that to differentiate phi n. Okay, where this phi n is phi composed with fn. So we're not going to distinguish a function and its pullback, or we're just rely on the context to tell us what it means. Oh, I'm sorry. So here this phi n is okay. So here this phi n is still phi constrained to a neighborhood of xn. Okay, and this equals to the same thing, the same summation integration. So in this formula, we first push forward x and then we differentiate. It is equivalent to we use xu to differentiate the pullback of this function, where this phi n is in fact phi the pullback. Okay, phi composed with fn. Okay. All right, so we can perform integration by parts on the unstable manifold. Remember that the SRB measure has smooth densities on the unstable manifold, so we can do that, integration by parts. And this tells us this equals to summation over n rho phi composed with fn, and then div u rho xu, okay? Where this is an unstable divergence within the unstable manifold under SRB measure. We're going to explain that in a minute, but let's first look at this term. Okay, this term composing with fn make this integrand looking suggesting that we can use decay of correlations to justify the convergence of the summation. Okay, and the reason of that is because without loss of generality, we may assume this phi has mean 0. And then composing with fn many times would make this function highly oscillatory around 0. And if you multiply that to another function, then this integration would become smaller and smaller as your oscillation becomes larger or more intense. Okay, and hence the decay of correlations justifies the convergence of the summation, but with a huge if this second function is regular enough. In particular, we want it to be Holder. We want it to be Holder continuous so that this integration decays exponentially fast and the summation converges. However, a priori, this xu is not even differentiable. Okay, so at the point of definition, we only know that this unstable divergence is a distribution, but not a function. Okay, however, later we're actually going to show that this distribution is indeed a Holder continuous function. But it is not yet. a function, it's not even a function yet. Okay, so in order to show that this unstable divergence indeed have enough regularity, let me first write down the definition of this thing. This is type U rho XU. This is defined as 1 over rho, and you differentiate rho in the direction of XU because the SRB measure is smooth along the unstable manifold, so you can indeed differentiate it along an unstable direction. So this term is legit, plus a divergence under the Riemannian metric. Okay, so there is no rho here, so this is just the divergence within the unstable manifold under the Riemannian metric. So let's first deal with this first term first. We know that to deal with this term, we use the fact that the SRB measure is the limit of evolving Lebesgue measures, okay? And using that, we can substitute this rho by the limit as the limit of Lebesgue measures, and that would give you an expansion. Okay, and then we can look at the expanded formula and do estimation in each of the terms and say something about the convergence and the regularity of the entire expansion. Okay, so we're not going to show the formula yet, but at least we can see that this first term can be dealt with. And now the difficulties are all in dealing with this Lebesgue unstable divergence. And in terms of computations, there were several previous work introducing various approximations on the unstable divergence. The first to mention is the F3 algorithm. This is developed by Wang and Chandramurthy. Okay, so the rough idea is to say that we can use finite difference to approximate this Lebesgue unstable divergence. However, if you remember, this XU is not really differentiable. So if you use finite difference to approximate it, this is going to cause numerical instabilities. Okay, so another way to approximate is in the blended response algorithm. And this is developed by Abramov and Andrew Maeda. Okay, so this was developed for a slightly different situation, but the idea can be carried over to our problem. And the main idea is to say, since the XU is not differentiable, why not we just replace it by something that is differentiable and can be easily differentiated. For example, let's replace the rough quantities by a Gaussian distribution. Okay, so after you do this replacement, you can carry on and do actual differentiations. Okay, nevertheless, both algorithms introduce various approximations, and those algorithms end up being approximate algorithms because the lack of analysis on the unstable divergence and the unstable contribution. Okay, we're not going to stop here. Okay, we want an accurate algorithm, and the way to obtain that is by two steps. The first step is we're going to seek to expand this unstable divergence. And using the expansion formula, we can do two things. First, we can show that this unstable divergence is indeed has some regularity. The second is that that expansion formula is going to be the starting point of designing an algorithm. Okay, the second step is to look at the expansion formula and seek to recharacterize this formula by some clever properties. Okay, so that's what we're going to do next for the unstable contribution. And that, the main technique would be to transform to a volume ratio. Then expand. Okay, and this work is due to Ruel and also due to Charles Pugh, which is a Berkeley professor, also due to Anosov, And I also want to warn you that the definition you see in this talk, I slightly tweaked the definition to make it coordinate free so that it better suits for computational purposes. And so it's slightly different from the original definition, but it's equivalent. But it's coordinate free, so it's better. Okay, so let me draw a picture. This is an unstable manifold going through the point X. For any point Y on this unstable manifold, we can flow according to the vector field X, which is a smooth vector field, for a distance of Q. And the endpoint we denote by Kc Y, we denote by eta YQ. Okay, so for fixed Q, we get a new U-dimensional manifold, which we denote by VUQ. And this map, eta, also defines the push-forward operator, and let this E be an unstable hypercube on the unstable manifold. This means that this E equals to wedge product E1 all the way to EU, and we call this an unstable hypercube, and this belongs to the spaces of unstable hypercube. This means that each vector are unstable, okay? And this space of all unstable hypercubes are only one-dimensional, okay? Because it is U-dimensional cubes on U-dimensional manifolds. So this is the one-dimensional subspace. And we also choose E to be normalized. Okay, so now this eta map defines a push forward operator which push forward a vector field on VU to a hypercube field on VUQ. Okay, and we denote this new vector field by eta star E. Okay, and let's define another map. So going through this point X, there is a stable manifold, which is basically defined similarly as the unstable manifold. And we define its intersection with VUQ as Kc XQ. Okay, so this Kc map for a fixed Q also maps X to VUQ. And it push forwards this vector field E onto a vector field on VUQ. Okay, and we denote that vector field by Kc star E. And for fixed Q, both eta star E and Kc star E are U-dimensional hypercubes on this VUQ. And because that subspace is only one-dimensional, so we know that this eta star E is parallel to Kc star E. And hence, there is this claim that the unstable divergence that we're interested in can be written as, so now because these two hypercubes are parallel to each other, we can define its ratio, and this ratio is a scalar function. And we can differentiate this function in the direction of xs. And that would be the unstable divergence. And this equivalence holds only true on VU. Okay, so this is a basic Riemannian geometry fact if we assume that this stable manifold varies smoothly to X. Okay, so this is elementary, but not easy. If without this assumption, we can still make sense of this equivalent in the sense of distributions, but now the caveat is that both XU and the eta and C star E are not differentiable. And nevertheless, we have transformed this unstable divergence to a new quantity. We give it a new formula. Okay. And now the only problem is that this eta star E is rough. And we seek to replace this eta star E. The way to replace it is to notice that, so this is Ex. If we scale correctly, then this Ex and C star E would all be pointing from your base stable manifold to a nearby stable manifold. Okay, so this is another stable manifold of adjacent point, say X plus delta X. And by the definition of stable manifold, we know that if we evolve these 2 points forward in time, they collapse. And if we evolve these 2 points forward in time, they also collapse. And hence we know that if we evolve this vector forward in time, and we evolve this vector forward in time, they become the same vector. Okay, this means that we have this limit relation. That is, if we push forward C star E, and we also push forward E of X, many steps, and then this ratio becomes 1.
I think we can only see the left half of your screen right now.
Oh, okay.
Okay, that's better.
This is better?
Yeah.
Okay. Let's see. Ah, okay. Oh. All right, so now we have this limit, and we can use this limit to have an expression for this rough term, and substitute into this this expression, and then we obtain an expansion of this unstable divergence. Okay, so we're going to show the expansion a little bit later, but in order to understand the terms in the expansion, let us first look at some definitions. Okay, these are not standard definitions, so I'm giving you some warning here. The first thing to define is the second order tangent equation. Okay, this goes by many other names, such as the Leibniz rules for the Riemannian connection of the push-forward operators. Let me remind you that this push-forward operator is in fact a tensor. Okay, so it is not a conventional tensor, because what it does is that it takes the vector at this point and pops out another vector at another point. Okay, so if you want to make sense of this as a tensor, you should feed it a vector at this point and then a covector at another point, and that would generate a scalar field as a typical tensor. Also, so this tensor is not conventional, but nevertheless, you can imagine that the things you do to typical tensors can be carried over to this push-forward operator as well. In particular, we can define the Riemannian connection of this push-forward operator. Okay, so in Euclidean space, this F star would be the Jacobian matrix, and this nabla F star would be the derivative of the Jacobian matrix, or the Hessian tensor. Okay, and this derivative of matrix for Riemannian manifolds is defined by this relation, this Leibniz rule, actually. So if you differentiate the push forward of E in the direction of F star Y, this equals to, if you first differentiate E and then you push it forward, plus if you first differentiate this matrix and then apply this on the vector E. Okay, so this relation is the Leibniz rule on Riemannian manifold. Okay, so looking at this, the form of this equation, we define a renormalized second order tangent equations, beta y of r. This is defined as, you first push forward r, and then you add the derivative of this matrix, you apply this on E, and then you further divide by the volume of the push forward of unit hypercube. Okay, and this beta, it will be referred to as renormalized second order tangent equations. Okay, it satisfies a particular type of linearity, that is beta y1 r1 plus beta y2 r2. This equals to beta y1 plus y2 applied on r1 plus r2. Okay, so this is the definition of renormalized second order tangent equations. We also define projection operators. We know the definition for single vectors. Let's say this is the unstable subspace. This is the stable subspace. This is a vector, small b, okay, which is a single vector. So we can define its projection. First, we can define this vector as p parallel b, and define this projected vector onto the author normal complement of Vu as p perp v. We can also define two oblique projection operators. This vector is PSV, and this vector is PUV. Okay, so these are all defined. These four projection operators are all defined for single vectors. And we want to do it, we want to extend this definition to derivatives. Okay, so the derivative of E will look like this. It is a summation of terms where each term is a wedge product. Okay, so all of the terms are unchanged except for one term in the middle that is changed to the derivative of EI. Okay, so in each summand, there is only one exceptional terms, and the way to define the projection operator applied on this derivative of hypercubes is to apply the projection operator on this exceptional vector. Okay, so that's the two definitions we need to look at the expanded formula. Okay, and that formula is copied down here. And our next step is to recharacterize this expanded formula for unstable divergence and hence for the unstable contribution. This is my work. Okay, let's denote this phi, define phi, psi actually, as a summation of phi, where this n goes from minus w to positive w, phi of n, where phi n here is phi, the pullback of phi. Okay, and psi xk is just a psi k xk. So this is the vector. Okay, so this formula is the expanded formula. And looking at this formula, all terms are well defined and all terms are honest functions. And hence, we can bound, by bounding each term in the summation, we can come up with some statement about the regularity of the summation and hence the convergence of the summation. Well, actually, that's reversed. We can talk about first the convergence of the summation and talk about the regularity of the summation. Okay, so but we're not going to do that in detail. Rather, let's just start immediately to recharacterize this complicated looking formula. Okay, so remember that if you push forward an unstable hypercube, it is still an unstable hypercube due to the invariance of the unstable subspace. Okay, so this means that this term equals to the unit unstable hypercube because it is divided by its norm. Okay, and this would be a hypercube at your zero step, so that's in the same space as E. And they have the same norm, so they must be the same. And this cries out for us to pull out this term out of the integration and see what is left over for us. And we can define this term as pk and define this vector as v tilde k for k positive. We can notice that this term relates to pk by a renormalized second order tangent equation whose second order derivative is taken in the direction of v tilde k. We can define this term as pk prime, okay, and define this vector as v tilde k prime. Again, we can notice that this term relates to pk prime by a renormalized second order tangent equation whose second order derivative is taken in the direction of v tilde k prime. Okay, and let's define a new quantity p as summing for positive n's pk perp. So this is to apply the orthogonal projection operator on p, which is a derivative of hypercubes. Subtract summation over negative n's pk prime. And using this newly defined quantity, we can express the unstable convergence by a very simple formula, okay? That is, this unstable contribution equals to rho beta v tilde applied on p plus psi 1 e1, I'm sorry, nabla e1 x1, and use this to inner product with e1. So this is inner product between two hypercubes, where this v tilde is defined as, for positive n's, the summation over v n, and subtract negative n's v n prime. Okay, so the way we obtain this v tilde, let me remind you, is that we first split this psi x into stable and unstable components, and then we propagate the stable components into the future and unstable component into the past, and then we collect and add all of these propagated perturbations. So this is the same procedure as we defined the shadowing direction. Okay, except for that, now this v tilde is not the original shadowing direction. It is a modified shadowing direction of source terms psi x. And this v tilde can be easily computed by the Niels algorithm we just introduced. Okay, so this is the first thing we know from this formula and this p. The second thing we know is that this p1, which is p at your next step, can be easily expressed. So there is an inductive relation between p1 and p. Okay, that is your p at current step, your p at next step is equals to p perp. So this is the orthogonal projection operator applied on this term. Okay, so this p actually satisfies a very simple inductive relation. It satisfies this renormalized second order tangent equation. And then we know that we can also see that due to the rescaling in beta, this inductive relation of p is stable. Okay, if you remember, when we define beta, in beta we are dividing by the growth of unstable hypercube, which is larger than 1. So that makes this inductive relation stable. This means that no matter what the initial condition you started with for your p, for a sequence of p, you can just apply this inductive relation, and eventually your Pn will be correct, regardless of where you started from. Okay, so in reality, oh, and by the way, another thing is that now we can also show that this p is bounded. And hence this entire integrand is bounded. And this is really good news because it means that we recovered the ergodic theorem kind of situation. This means that we can use the average over a trajectory to replace the average over the SRB measure. And this is going to give much faster convergence than the original linear response formula. Okay, so we are about to develop a good algorithm. And in this algorithm, so to compute the unstable diversion, let me say it again. We only need to start from any initial conditions, say 0, and then we apply this inductive relation. And then eventually we get the correct sequence of P, and then we can average over one trajectory to get the unstable contribution. Okay. And there is also a computational point that is the renormalization. We only need to do it intermittently. We don't need to do renormalization at each point. So that makes the induction more even more efficient to implement. Okay, so let's summarize what we have done so far into the linear response algorithm. The first thing we did is we decomposed the linear response into two parts, the shadowing contribution and the unstable contribution. For the shadowing contribution, by a novel recharacterization, we see that it can be efficiently computed by this Niels algorithm, okay, where the main computational cost is in solving many first-order tangent equations. For the unstable contributions, we spend a lot of effort. We first went through several transformations. We integrated by parts. Then we changed the measure from SRB to Lebesgue for the unstable divergence. And then we changed the Lebesgue unstable divergence to a volume ratio. And then we expanded the volume ratio. And then we got the expanded formula, and we recharacterized the expansion by some novel properties. That is, the unstable contribution can be easily expressed by this renormalized second-order tangent equations whose derivatives is taken in the direction of v tilde, where this v tilde is the modified shadowing direction, which again can be computed efficiently by the Niels algorithm. So we use the Niels algorithm twice in this linear response algorithm. Okay, so once in the shadowing contribution, once in the unstable contribution. And the total cost for computing the unstable contribution is now many first-order tangent, that is the Niels algorithm, plus many second-order tangent equations. Okay, that's the cost associated with this beta, which is second-order tangent equations. Okay, so now we have an algorithm which is accurate and it is fast for computing linear response. Let us look at an application. Okay, so we apply our algorithm on this dynamical system. It's got three variables. The first variable is a stable variable because at each step, we're multiplying by a factor smaller than 1. The second step, the second and the third variable are unstable variables because we're multiplying by a factor larger than 1. And we also have some interactions between the first variable and the second variable, and between the first variable and the third variable. Okay, so this makes things more complicated. And this problem, although it looks simple, it is actually difficult for previous method. It is difficult for paper pen analysis because we cannot tell the direction of unstable and stable subspace beforehand. It is also difficult for approximate algorithms because look, we have 2 out of 3 unstable directions. So hence, it would, for previous approximate algorithms, they introduce various approximations on the unstable directions that would make the error pretty large for this particular problem. Okay, this is also difficult for ensemble method because you see at each step, the unstable hypercube grows pretty fast, okay, by these factors. Nevertheless, okay, and let me say, so these 3 pictures on the bottom are the distribution of the empirical distribution of one trajectory of finite length. Okay, and you can see that this attractor is actually pretty a fractal. So the problem is actually pretty difficult. Nevertheless, the linear response algorithm is capable of giving you the correct result efficiently. Okay, so this is the result. The vertical axis is the averaged objective. This is the parameter of the system. And these dots and lines are all computed using the same one trajectory. And the dot is the objective averaged on this trajectory. And the line is the derivative computed by the linear response algorithm. Okay, as you can see that the linear response algorithms reveals the correct trend between the objective and the parameter with only one trajectory. And if you want to reveal the same trend by finite differencing over a collection of data, then you need roughly 20 data in order to adequately tell what is the, to tell this trend from interpolating those data points. Okay, and this is very encouraging because overall, the linear response algorithm is a few times faster than this finite differencing method. And this recovers the non-chaotic cases where, if you remember, computing the derivative function should typically be a few times faster than finite difference. Okay, also there are also some other benefits, but it is a few times faster than finite difference. And we recover this for chaotic situations. We find an algorithm which is also a few times faster than finite difference. And this is encouraging because it hints that perhaps the linear response algorithm is very close to the optimal efficiency for differentiating chaotic systems. Okay, and this advantage is because we have carefully analyzed the shadowing directions and unstable divergence, and we give them novel characterizations. Okay, so the advantage of this linear response algorithm, let me summarize. It works on manifold, which is not Euclidean. It works for any unstable dimension. Its cost is only OU, and it is proved rigorously for uniform hyperbolic systems. Okay, and there is a remark here that we can trade off this cost to either OU square or some higher cost, so that although this cost is higher, but it becomes less or independent of the number of parameters and objectives. So eventually, those variants are better for cases with many parameters or many objectives. Okay, so it is pretty good that the linear response algorithm has all of these four properties, and no previous algorithm has these four properties altogether. In fact, I know, certain algorithms, they don't satisfy like none of the properties. So the linear response algorithm is pretty good. And it is, I think it should be the fast, accurate algorithm for differentiating stationary measures of chaos with fractal attractors. And it should also be the first such algorithm, but this certainly depends on your opinion on finite difference. If you think finite difference is accurate, or the ensemble method or operator-based method are accurate, because those methods are theoretically accurate, but in reality, you cannot really afford for the convergence to actually happen. Okay, and nevertheless, the linear response algorithm should be the fastest accurate algorithm for this purpose. And this is all thanks to the careful analysis and the novel recharacterizations we have done to the shadowing direction and the unstable divergence. And those two objects are the central objects in the linear response theory. And we have dealt with it very satisfactorily. Okay, this finishes my talk, and I'll take some questions.
May I ask a question?
Sure.
Can you go back to the slide you showed how to deal with the unstable manifold, the divergence over there. Yeah, that's over here.
Yes.
Yes, I guess I don't quite understand the equation on the last second line over there. And you're saying XU is the factor field on the manifold.
Mm-hmm.
And then the divergence with over there is XS applied to this one over here.
Yes. Yes.
Yeah, I didn't see this one in your paper over there. So this is something recent, is that right?
I'm not sure which paper you are reading. It is in the recent paper, linear response algorithm.
It's the approximate linear response
Not that
via shadowing.
Not that one.
Not that one.
Yeah, not that one.
Okay.
It is a recent result.
Mm-hmm.
Yeah, and this is like a Wells work, and in Wells' paper, he actually acknowledged you for pointing out, the lack of regularities. I think you pointed out, and he came up with this technique to prove this unstable divergence actually is Holder continuous.
Oh, okay.
So basically, to convince, I think there is some like a formal argument I can convince you. So basically, you want to get a so this type U XU is a scalar. Okay, so and it is so on the right hand side, if you differentiate this eta star E, you can imagine that this is some derivative of X. If you define this C star E, you can imagine this is some derivative of XS. Okay, and on the left, it is a scalar. So the way to get a scalar out of these two derivatives is to do a contraction. And because you're differentiating a ratio, so you're subtracting those two contractions, and this gives you a contraction of XU. And that is the definition of type U XU. That is like a very formal and dirty argument.
And can you also move to the example you computed later slide over there a little earlier, because I didn't see the hyperbolic system you actually computed.
This one, this is the governing equation.
Okay. So you have dimension 2 for unstable, is that right?
Yeah. It takes about 1 second.
Yeah, I'm just wondering because in both examples, one over here and also the other one you had in the previous paper, rho essentially is just the big measure.
This one is not. This one is like a. This three plots on the bottom is the one trajectory, so it lands onto the attractor. So you can. I mean, this is two-dimensional view, but it's actually, if you take a three-dimensional view, it's still like only a two-dimensional, roughly a two-dimensional manifold. So it's like a 2 out of 3. So that's like a fractal in three-dimensional.
Okay.
Yeah, it's just the plotting issue. Like I cannot plot the
right, because
it looks a fractal.
So it's not a diffeomorphism anymore over here.
You mean F?
Yeah.
F?
The unperturbed map.
What? Yeah, it's not a diffeomorphism. Yeah, it's actually 2 to 1, right? Actually 6 to 1.
Right, right.
Yeah, it's an interaction between expanding circles and some like contraction.
Does it have an attractor? Say, is it so you have expanding rate is 6 and contracting rate is 0.05. Okay. All right, thank you.
Are there any more questions? If not, let's think on again.
All right.